Hello students, welcome to 7th lecture on complex numbers. In the last lecture we discussed the nth root of unities, and based on that we have proved several identities. Let us continue on this discussion. We have proved the one of the identity, which is sin pi by n, sin 2 pi by n, sin n minus 1 pi by n, value is n by 2 to the power n minus 1. Let us see that how this helps us to solve certain problems. Find the value of the following expression. The expression is sin 10 degree product with sin 20 degree product till sin 80 degree. We would like to find the product of this expression. So, let us try to use the above identity to find the value of this expression. What we observe is, given any n value, let us say n equal to 2, then what we see is that this is till sin pi by 2, and if I take n value let us say 10, then it goes till, say the first value will be sin pi by 10, which is sin 18, and till it goes sin of 9 pi by 10. Okay. So, if I try to identify with the first term where it starts with sin 10 degree, very naturally I see that if I take n as 18, then I am able to get the factor, the first factor, which is sin 10 degree. So, which means let us try to start with n equal to 18, then I am able to coincide with the part of the expression from the above identity. So, if I consider n equal to 18, what do I get? Here it is sin 10 degree, that is pi by 18, and other which is sin 20 degree, which is sin 2 pi by 18, and it goes till sin 17 pi by 18, whose value is, we have 18 by 2 to the power 17. Let us see whether we can further simplify it. The first observation is, if we take the k value here 9, or the ninth term here, which is, say here if I take k equal to 9, where my expression is above general term is sin k by 18, I take k equal to 9, we get sin pi by 2, which is 1. So, it means that the ninth term in this expression, ninth term value is 1. But the other observation is, this is observation 1, and second observation is, if we consider sin 18 minus k pi by 18, which is same as sin k by 18. In fact, you have a general observation, that is sin n minus k pi by n, this is same as sin k by n, k value from 1 to n. We have the given say expression, we have sin pi by 18, sin 2 pi by 18 until sin 17 pi by 18, which is 18 by 2 power 17. We observe the ninth term is 1 and remaining other terms are sort of repeating, in the sense that sin 17 pi by 18, which is same as sin pi by 18. So, we get the square sin square 2 by 18 till sin 8 pi by 18 square, which is say we can cancel the common term, which is 9 by 2 power 16. Now, this term is nothing but our required expression, that is sin 10 degree, sin 20 degree and sin 80 degree, and whole square is thus, and now you take the square root, we get 3 by 2 power 8 as the value. Now, similar to the identity, the sign products, we get n by 2 power n minus 1. Similar to this, we can get a identity involving cos term, which is cos pi by n, cos 2 pi by n till cos m minus 1 pi by n, which is equal to square root of m by 2 power m minus 1. So, now how to prove this identity? If I recall, when we proved the identity involving sine term, what we used is that the polynomial z to the power n minus 1 till this plus 1, this polynomial is factorized using the nth root of unity, and we have considered value of z as 1, then we got this expression. Then once you take its modulus value, then we got the sine expression. Now, the hint is use say z equal to minus 1 in this identity and do the similar procedure. So, when you do the similar procedure, when you are calculating the distance from minus 1 minus alpha power k, which is same as 1 plus alpha power k modulus, where you will get the cos term on the right hand side. Using this hint, you can show that the product term here involving cosine gives this value, and where n is a even number, if n is odd you get this expression, and combining the sine and cosine identities you can derive the identity involving the tangent term. Okay. So, I leave the proof as a exercise. Now, we will discuss the nth root of unity with a particular case n equal to 3, which is called cube root of unity. So, we consider n as 3 and we are asking what are all the complex number whose third power is 1. We know that we get the term which is 1, cis angle is 2 pi by 3 and the other term which is 4 pi by 3. The complex number which satisfies this equation are these numbers. Okay. So, there is a special notation which is omega, which is called the cis 2 pi by 3. We know what is the value of cos 2 pi by 3 and plus I sin 2 pi by 3. We get the value as minus half plus I root 3 by 2, and what we see is that the term, the next term is nothing but omega square, that is the cis 4 pi by 3 is just obtained as cis 2 pi by 3, which is nothing but our omega square. So, using this notation omega, so what we observe is 1 omega square are cube roots of unity. Very easily we can see that 1 plus omega square, the value is 0, because you can also observe that omega square is nothing but omega conjugation. Now, it is once you sum omega square, the imaginary part cancels, the real part of omega is minus half. So, you will get 2 times of real part, which is minus 1. So, the sum is 0. So, we see that it is remark 1, and similar to the say what we have done in the nth root of unity, omega power say n, where n is 3, which is we get it as just 1. Okay. So, one can just calculate, raise its power 3, which is here for example cis 2 pi by 3 cube, which is cis 3 basically goes in the multiplication in the argument, you get only 2 pi, that is 1. Okay. Or we can also see the geometric interpretation for this, that is consider the unit circle one and omega is placed by say rotating 120 degree, and omega square again you rotate by 120 degree, which is in fact the conjugation, which is omega square. It means that multiplying by omega, which is same as that adding 120 degree angle to this particular vector. Now, you add one more 120 degree, that is multiply by omega, you reach back 1. So, we see that omega cube is 1, and in general if you consider omega power say 3 power n, this is same as omega power 3 power n, this is 1, n being can be any integer. So, the observation is if we have omega power 3 multiples, it is 1. And one more observation what we made is sum of cube roots of unity is 0, like in general we have nth root of unity, you sum it up you get 0. Let us do a simple problem. Find the value of or simplify this expression in a way that it reduced to the form a plus ib. The expression what we see is that this term is nothing but our omega. So, using the property of omega we can simplify this easily. So, consider this term 4 plus 5 omega power 334 plus 3 times omega power 365. As we noticed before, this term can be written as omega power 3 multiples, which is 333 multiplied with omega plus 3 times. Again we can split the power such a way that one is 3 multiple, which is 363, this is omega square. So, this term is 1, again this factor is 1. So, what we get is this is 4 plus 5 omega plus 3 omega square. Now, again use the fact that the sum of cube roots of unity is 0. From this we get omega square is minus omega minus 1. Now, substitute in this equation, we get it as say plus 5 omega and then minus 3 omega minus 3, we get 1 plus 2 omega. Now, just see that what is the value of omega, which is minus half plus I 3 root 3 by 2, which is, after simplifying we see that here we get a minus 1 here and cancels with 1. So, the remaining factor is I times root 3. So, it seems that when we have say expression comes with the powers of omega, we could easily reduce by using the properties of omega. Let us do a one more problem. Now, we need to show that the power of this complex number, which is raised by 3 multiplied with 2n plus 1, which is always minus 1 for every n being an integer. So, let us try to see what is this expression first. Consider this expression root 3 plus I by root 3 minus I. Let us simplify directly, which means you multiply by its conjugate root 3 plus I root 3 plus I, we get here which is root 3 plus I the whole square divided by, this is 3 plus 1, we get a term which is 4. Now, recall the value of omega, omega is minus half plus I root 3 by 2. Now, we see that this expression almost close to this. This is equal to root 3, we can take out I commonly. If you take out I outside, which is I square, we can take 4 inside the square term, which means that we get here 1 minus by 2 now this is same as this is minus 1 and this is nothing but minus omega, which is we see it as omega square. So, now if we raise the power 3 times root 3 plus I by root 3 minus I 3 times 2n plus 1 and what we see is that here minus omega square power the 3 multiple 2n plus 1, this is minus 1 power 6n plus 3 and omega square we can write it as 6 power 2n plus 1. This gives us minus 1 and this gives us just 1 because it is multiple of 3 which is always 1. So, we are able to verify our statement. Let us do one more problem. We would like to find least positive integer n such that it satisfies this equation. So, there may be several n will satisfy this identity, but we need to give the least value of n for which this equation satisfies. So, by this expression we can use that 1 plus omega square is minus omega and omega power 4 which is just say omega cube multiplied with omega which is just omega. So, which means that this expression we get it as 1 plus omega square power n 1 plus this satisfies if and only if this is minus omega power n and this term is 1 plus omega which is minus omega square power n and this satisfies if and only if omega power n is omega power 2n. This satisfies if and only if omega power n equal to 1, we just cancel the omega power n. We are asking what is the least value of n which satisfies this, which is simply n is 3. Let us try to discuss a problem which is slightly different. We would like to ask what are all the complex numbers which satisfies this equation. So, the moment we see this, if we take z equal to 0, 1 is satisfied, which is a trivial solution. Now, let us assume z is non-zero and we ask whether any non-zero complex number satisfies this equation. Non-zero. Once it is non-zero, it has inverse or even the modulus of z which is non-zero, we can divide by mod z square throughout this expression. So, we get z square by mod z square plus z by mod z, say here one mod z cancelled and we get 1 this is equal to 0. Now somehow it is now comes closer to familiar equation, which is z by mod z the whole square and another complex number plus 1 equal to 0, which is exactly the omega where it satisfies this equation. So let us now ask our question again. We are looking for a non-zero complex number which satisfies this equation. So if I consider a number omega as z by this, then the omega should satisfy this equation, and we know that there are two unique solution to this equation, which is nothing but the cube root of unity, which we called as omega, so and omega square. So it has two solutions, which is cis 2 pi by 3 and cis 4 pi by 3, which we call it as omega and omega square. Now if we consider z as lambda times omega, where lambda is a, so what do you get from this equation? So we can choose z by mod lambda as omega, it satisfies this equation. So we just put the value for z by mod z, which is omega, where mod z can be arbitrarily chosen now. So which means z can be written as lambda times omega and other say lambda times omega square, or where lambda is non negative. So our solutions to 1. Let me again repeat what we have done. First we observed z equal to 0 is a solution, and then we look for a non-zero solution. Once we assume z is non-zero, we are able to divide by mod z, which means our equation scaled onto unit circle, because whatever complex number which satisfies this equation whose modulus is 1. Okay. So we are looking for a complex number which is lies on the unit circle and satisfies this equation, and that is nothing but the cube root of unity, and from that we derived all other solutions. Now let us try to discuss on the advantage of this complex numbers in terms of geometrical aspect. Okay. So the cube roots of unity, it has a geometrical interpretation, that is when we take the unit circle, we place 1 here and omega with 120 degree angle to the positive real axis, and other you rotate by the same vector by 120 degree, we get omega square. What we know is, if we place a polygon with the vertex as this cube roots of unity, here polygon with 3 sides, which is nothing but the triangle, which is regular, here regular, it means that we are getting a equilateral triangle. So the equilateral triangle, let us try to recall what is equilateral triangle. So, triangle with all sides are equal, that is the, say let us call it as, this is the length of the side is A and the other length is B, and thus if it is equilateral then all sides are equal, and also all angles are equal. Not only that, we observe here that this equilateral triangle, the centroid coincides with the orthocenter as well as circumcenter. So, we can list several properties for the equilateral triangle. For the time being, let us just take one of the definition, that is all sides are equal and all angles are equal. Any one of them you can take as the definition. These two are equivalent to say that a triangle is equilateral triangle. Now, it is very easy to verify that the triangle which we obtain here is an equilateral triangle simply by seeing what is the sides length. Sides length are, that is 1 minus omega. You could see that this is same as omega minus omega square. Why? Because this can be written as, omega can be taken commonly, and what you get is omega product with 1 minus omega, and the modulus can be taken for each factor, mod omega is 1. So, you get that this is 1 minus omega, which means that the side and this side length is equal. Similarly, you can see that this is also equal to 1 minus omega square, which is just you can multiply by mod omega, then you will see that immediately it is equal to the other side. Okay. So, we could directly verify that the triangle placed with vertices as 1 omega omega square gives us equilateral triangle. Now, using this property of cube root of unity, we will prove some characterization of equilateral triangle. We prove the following, that is a triangle T with vertices are denoted by A, B, C, where the A, B, C are in complex numbers, and we say that T is equilateral triangle if it satisfies any one of the condition. Otherwise, if any of the one condition satisfied, then T is equilateral triangle. Let us read what is this condition. A plus omega times B plus omega square multiplied with C, their sum is 0, and the other equation is A square plus B square plus C square, that is equal to AB plus BC plus CA. If this equation satisfied, then we can claim that the corresponding triangle with vertices as ABC is an equilateral triangle. So, let us try to prove this result. First, let me prove that if T is equilateral triangle, then we show that it satisfies this equation, and similarly if the equation satisfied, then we can claim that it is equilateral triangle. So, we will show that 1 and 2 are equivalent statements, 1 and 2 are equivalent statements. So, what is given to us? We are given with a triangle which is placed in the organ plane somewhere with vertices here A, B, C, with the orientation is, one need to notice the orientation in the anti-clockwise direction. Now, when it is given that it is equilateral triangle, what we know is the angles are equal. Or we could also see that the length of each side, they are equal. Okay. Now, I am going to observe that, is it really a, like, can I study the triangle by shifting to some other point, okay, the same result, can I shift this triangle to some other point and solve the problem there, and can I come back, okay, which is naturally called as shifting property. If I, so what is our claim now? First we assume that it is an equilateral triangle, then we show that the second part. What is the second part? This is A plus omega times B plus omega square times C equal to 0. We would like to show this. So, if I shift this triangle, it means that I am going to add by some complex number to all points, otherwise you subtract by a point by each points in this particular triangle. Meaning is, just consider that, let us say that you have a triangle with vertices as, let us say that it is at 1 comma 1, and let us say this is 3 comma 1, and let us say this is say 2 comma 1 and half. Okay. So, what I could do is I can subtract by 1 comma 1, then the entire thing can be shifted to the point origin. Okay. So, you subtract 1 comma 1 to every point in this triangle. So, which means I can create a new triangle here without changing any orientation and as well as the side length. So, without changing any geometrical property, we can just shift, which means we can just taking a triangle and place it in the other place. Okay. So, what I can see is that if I shift, will it be still this equation, whether it will be invariant, okay. That is, suppose the equation is satisfied, suppose suppose 1 is satisfied, okay, then will it be same as true for a other triangle which was replaced to some other point, okay, which means my new point is A minus Z, B minus Z, C minus Z, they create a new triangle which was just shifted by Z. Okay. Now, I am asking whether the equation will be satisfied, just try it, substitute in the equation for this particular point as vertices. So, which means it is A minus Z plus omega times B minus Z plus omega square C minus Z, which is same as A plus omega B plus omega square C minus Z as a common factor 1 plus omega square, which is 0, and since the equation satisfied for A, B, C, we see that this is 0. So, now what we observe is, if A, B, C satisfies 1, then you can shift it to any other place by just subtracting by Z, again it will satisfy this equation. On the other hand, so it is a vice versa, if this particular one is satisfies equal to 0, you can actually show that the one is satisfied. So it is like this is call it as 2. So what we observe is 1 and 2 are equivalent. Okay, from this observation what we are going to do is, we are going to, without loss of generality, we are going to shift our triangle to a origin as centroid to the triangle. It means that I am going to shift my triangle such that origin as the centroid. What we know the property of equilateral triangle is, origin, say the centroid and circumcenter are equal. So what we know is, so we have actually shifted, let us call it as, it is a notation abuse, but just it is a, the property is invariant under this shift, I call it as, again this is ABC. Now what we observe is, the angle between these each vertices which makes 120, because this angle which is 60, they are equal angle because of equilateral triangle, and since the center is, what we see is that it is centroid as well as the circumcenter, we see that it bisects, this angle is, this particular line bisects the our original angle. So which means this is 30 and the other one is 30, so remaining will be 120. So from this observation what we can see is that this side vector which is b minus a, if you rotate by 120 degree angle, so if you rotate 120 degree angle, it will reach the side which is c minus b. So now this observation gives us that in fact it will be equilateral triangle if and only if my side c minus b is achieved by rotating b minus a by 120 degree angle. So which means that T is, the triangle T is equilateral if and only if we get our side c minus b by rotating, the rotation is nothing but multiplying by omega thus. So this is same as, now we see that by simplifying the equation which is c plus a omega and then minus b 1 plus omega, this is equal to 0 and this is same as a omega b omega square plus c, this is equal to 0. Now to get our equation just multiply by omega square, then we get here it is omega cube, that is 1, here you will get omega power 4, that is omega thus. So this concludes that the first remark we are able to achieve that T is equilateral triangle if and only if it satisfies this condition. Now we would like to prove the other one, that is T is equilateral triangle if and only if thus. So once T is equilateral, which means automatically it satisfies this equation. So we will just show that these two equations are equivalent. So, let us prove that 2 is equivalent to 3, or what we are basically like equilateral triangle if and only if the condition 3 is satisfied. Again one can notice that if the vertices, again the shift property again holds, that is if you shift ABC, that is the triangle by Z. So, if this is satisfied if and only if B minus Z square plus C minus Z the whole square, this will be equal to A minus Z, B minus Z plus B minus Z product with C minus Z plus C minus Z thus. So, now again what we are going to do is we are going to make a slight convenience, so that our equation looks very simple. Simplest choice, we will just make the change by Z equal to A, which means shift the triangle T such that one of the vertex as 0. Okay. So, which means without loss of generality we can assume 0, B, C are vertices of T. Now, which means that it satisfies the equation which is given to us, that is B square plus C square equal to BC. Now, our claim, what is the claim we would like to make? Claim is this is equivalent to satisfying the condition 2. Let me recall what is the condition 2. So, if the vertices are A, B, C, then this equation satisfies. Now, our vertex A is 0. So, which means we reduce to the equation, this is equivalent to saying that omega times B plus omega square C, this must be equal to 0. Now, ask what does this mean? This is equivalent to saying that we need to say that here just observe that omega is minus B by C. To show that B square plus C square equal to BC, this is if and only if, now it boils down to showing that minus B by C is cube root of unity. Now, this equation what it gives us is B by C plus C by B, this is 1. From this we have an expression for B by C, this implies that B by C is 1 minus C by B. Now, we can try to claim about B by C is cube root of unity. So, for this, so our claim is minus B by C cube is 1. So, for this start with minus B by C square, which is same as B by C product with B by C, but B by C is 1 minus C by B. Now, notice that this we get it as B by C minus 1. Now, again go back to the expression B by C minus 1 is minus C by B. Now, it is clear that y minus b by c cube is 1. So, minus b by c square multiplied with minus b by c. The first term we got it as minus c by b and product with minus b by c, which is 1. Hence, we concluded that minus b by c is cube root of unity. Hence, we are able to show that the following equation satisfies, that is, the triangle with origin as one vertex, other vertex BC, it is equilateral triangle if and only if these two equations are satisfies, but we know that once this equation is satisfies, then the triangle must be equilateral triangle, which we claimed before. So, hence we proved that the following assertion: T is equilateral triangle if and only if it satisfies any one of the condition. So, in this lecture we discussed several properties of cube root of unity, and we discussed several problems based on the cube root of unity, and we discuss some more problems in the next lecture. Thank you.